Welcome back and good morning once again. So, in the last class we have introduced the concept of finite order distributions and we classified the class of all finite order distribution which can be realized again as a dual space by changing the topology on C c infinity of omega. So, again repeat, when you say d omega, it is a one particular topology introduced in the beginning and is also introduced in our preliminaries. So, there is df of omega, it is a different topology, but the same space C c infinity, but then the topology. So, the topology basically changes the space. So, the elements are not just the factor, you have to look at it. So, now we will go to the next important concept, support of a distribution. Support of a distribution. So, whenever we are defining a new concept or a concept to distributions, you should get motivated with the distributions given by locally integrable functions. So, you see a definition in the locally integrable function, that particular notion, and see when it is comes to the distribution given by that locally integrable function, whether that definition can be generalized. Is there any problem while generalizing it? That is the way we should look at all the time distributions. So, let us start with a locally integrable, let f equal to motivation, let f is equal to f is in L1 log of omega. As usual, omega is an open set which we are repeatedly using it, and then what is your Tf of phi? Tf of phi, the distribution given by phi, is equal to integral of f phi over omega. Now, what is the now the definition of f, the support of f? Support of f, support of f. You would have seen one definition that you take the set of all points x such that f x not equal to 0 and close it. So, it is a closure of the set of all points such that f x is not equal to 0, but that definition is not possible to extend to distributions because distribution is not defined point wise. Indeed, the support of a distribution is also going to be the subset of omega, not subset of d omega. But this definition of point wise understanding of a function cannot be generalized, it is not possible directly to generalize that one. But then there is another definition, it is the complement of the largest open set, complement of the largest open set, where f vanishes, where f vanishes. Okay. So, this is the definition. So, you have to understand what is the meaning of t vanishes, what is the meaning of, is a very interesting concept, meaning of a t vanishes in an open set, vanishes in an open set. Okay. Suppose now here take this one. So, f vanishes, suppose f vanishes. So, we are trying to understand Tf first before coming to T. Suppose f vanishes in an open set, omega naught contained in omega. Okay. Then you can see that f vanishes on an open set, then if phi is in d omega and support of phi is in omega naught implies Tf of phi equal to integral of f phi over omega. See, f vanishes in omega naught, but support of phi is in omega naught, that means phi vanishes outside omega naught. So, essentially this means this one. So, if you have seen my earlier discussion in the beginning of the whole thing, so the vanishing of an function f is equivalent to telling that one this fact. Okay. So, if Tf of integral of f phi equal to 0 over omega for all phi in d omega with support of phi in omega naught, then f will be 0. So, this is a defining condition of f vanishing. So, the vanishing of f pointwise that f x equal to 0 for all x in omega naught can be written in terms of, and this is a generalizable condition. So, that is a definition exactly. We say T, now it need not have to be this definition, you can say it may not be integrable, but you can apply to any distribution T. We say T in d prime of n omega vanishes in omega naught in an open set, of course, in an open set omega naught contained in omega if T of phi equal to 0 for all phi in d omega with support of phi is contained in omega naught. You see, same definition. So, that is advantage when you see the function you are going to as a mapping, okay. And that leads to the definition. So, for T, this another definition for support of T, support of T in d prime of omega. For T in d prime of omega, support of T we denote by sub T, okay, is the complement in omega, okay, that is complement in omega of the largest open set where T vanishes, So, look for all open sets, that is the best way. Look for all open sets in omega where T vanishes, that is a definition according to this definition, and then take the union of that, then you will get the all the largest open set, and you take its complement, and that is the thing. Another definition immediately, if support of T is compact, the support of T of course contained is compact, then we say T has compact support, say T has compact support. Okay. So, immediately you need examples, right. That is how you work with. You look for all examples, whatever distributions I know. One, of course, support of all delta k. What is that? Delta k, delta L, this is 0. It's easy to verify, right? For all L equal to all Dirac delta and all its derivative. That is true, right, because trivial, right, because delta L of phi is equal to minus 1 power L phi power L of the nth derivative at 0. So, if you have your function here, you look at take any open sets. So, minus infinity. So, delta L vanishes on R minus 0, which is an open set, and this is the largest open set, does not vanish away. If phi 0 is phi 0, it is a definition, you see, it will go there. So, that is one thing. 2, suppose t is equal to t of given by a continuous function f, given by a continuous f, then support of t is equal to the support of the function. So, you see as a function which you have the definition. Yeah. So, this is a small exercise, result is not true, trivial result is not true in general for general f, I think, for general f. Okay. Construct an example, easy, there is nothing difficult about it. So, you do not have any things. Later you will I do not know, I will prove it, at least you will say that every distributions with 0 as support can be written as the linear combination of this Dirac delta. So, the singleton given by that is essentially the Dirac delta and its derivatives. Okay. So, this immediately tells that this is a compact, and this example immediately tells you you can construct sets distributions T with the non-compact set. It depends on the support of f. So, you can have the other derivatives. Okay. Now, we maybe I will go to, yeah, maybe I go there. So, let me give you a new notation. This is used in distributions mainly. This is also considered as C infinity of omega. Okay. It is a notation which used here, and then you have a topology on here, right. There is a topology which is already, you know, that a sequence converges. You have also know that this can be defined as a locally convex topology, which we already explained in the preliminaries, given by a family of seminodes. Okay. So, with that means that phi n converges to in C infinity converges, it's all its derivative converges to 0 on uniformly on compact sets. D omega, you can also have the condition that there is a compact set it belongs. This we do not do that. With respect to that, this of course is contained in D omega embedded continuously. So, the convergence in D omega implies convergence in E. And then you can also, with the respect to topology, you can also talk about E prime, and E prime will be, it will be smaller, D prime of omega, you see. So, what does that mean? What do you mean by E prime contained in? Means E prime, if T is in E prime, D is contained here. Yeah, T is in C infinity of omega, it is defined on C infinity of omega, but then that contained here T going to T as a identity mapping, that is always the inclusion. It gives you the corresponding topologies, and it is a continuous inclusion. The injective mapping is basically continuous. So, the aim is to characterize E prime. Aim is to characterize trace E prime. See, these are all. So, you see these are all can be special distributions, right. So, if you have a, so you look at that one, if you take T is in T prime, these are some passing comment, if T is in D prime, it means that T is defined only in D omega, okay, D omega to R. But the question is that can we extend T to T tilde, initially denoted by T tilde, but later we will not use, we use the same extension. Can we extend T to E, because E omega is a bigger space. That means can we extend every distribution to a bigger space, then T will be in E prime, that is the meaning of it. That cannot happen because E prime will be much smaller. So, what are all those distributions which can be identified with E prime, and what we are going to see that E prime can be identified with the set of all distributions with the compact support, okay, and that is what we are going to do that. So, that is the theorem. So, there is an extension taking place all the time, and you know that even a density, if you want to extend, this is a general function analysis result, if you want to extend from a smaller space to bigger space, even if it is dense, in the small space it would have given continuity, but you have to verify continuity with respect to the other norm. If you do that, you can extend it. So, that let T is belongs to T belongs to D prime of omega, has a big let me see, suppose has compact support. If it has a compact support, okay, then T can be extended to E omega as a continuous linear function, as a continuous extended to continuous linear function. So, first time functional denoted by D tilde. Later, so T tilde is a mapping from E omega which is continuous, that is T tilde is in E prime of omega. As I said, later we will not use T tilde, we will use the same T as an extension. Conversely, if T is in T tilde is in E prime of omega, then T, that means you can restrict T tilde to E omega to D omega, you can restrict because it is defined in a bigger space. So, you can restrict T restricted to omega is in D prime of omega, and that T has compact support, that is the meaning of that T has compact support. This is an important result, and there are some observations and other things. I will give a proof of it. So, more than the proof, the important things are observations and facts and certain tricks which we will be using again and again. So, the first one is an observation. this is a some sort of a local nature, okay. Because t is defined, t is a linear function, so it is defined globally. You want to understand locally little more about it, okay. Suppose phi 1 phi 2 belongs to, this is trivial, but it is a very very important observation, belongs to d omega, and phi 1 is identically equal to phi 2 in a neighborhood of the support of t. So let t is in d prime be a distribution, any distribution, okay, nothing like compact support, neighborhood of the support of t, then t phi 1 equal to t phi 2, then t of phi 1 equal to t of phi 2, okay. That means if you have a so you have your domain omega and you have your support of t, this is your support of t, okay, no compactness or anything, and then you are defining in a some any neighborhood, how big does not matter, okay. This is the neighborhood where here the whole area here phi 1 equal to phi 2. Then it does not matter how phi 1 and phi 2 behaves outside that, the behavior is the material of phi 1 and phi 2, whatever it is, okay. This is trivial, right, trivial, since if you consider phi 1 minus phi 2, then support, because phi 1 equal to phi 2 in a neighborhood, then support of phi 1 minus phi 2 is outside that neighborhood, support of phi 1 minus phi 2 is outside the neighborhood. In other words, phi 1 minus phi 2 vanishes outside the neighborhood, okay, that is it. And then that means phi 1 minus phi 2 vanishes in that neighborhood, that implies immediately by definition t, that is a definition of t of phi 1 minus phi 2 equal to 0. But t is linear, that implies t phi 1 is equal to t phi 2, okay. This is a very very important thing. Now let us try to give the proof of e prime of omega is identified with the set of all t in d prime with this is a theorem, I am writing it in a much more, support of t is compact. Proof is not easy, proof is very easy. So this way, one way will this way we will prove. Assume t is in d prime and k is equal to support of phi is compact. So again I use a trick, this is a kind of a trick, you may use it later also. This we continuously use a trick. So choose this, you may have to do these tricks throughout this course. When you choose phi naught is in d omega with phi naught identically 1 in a neighborhood of k. So k is the support. So you have your again the same picture, and you have your k, that is where the support, and then phi naught is choosing in such a way that phi naught is equal to 1, identically 1 in this entire area. Okay. Then what you can see that immediately define, I will tell you this one. Now define, you want to extend it, you want to see that it is in E prime of omega. So define T tilde from on E omega to R by T tilde of phi is equal to T of phi naught. Okay. Look at here, phi is in E omega. So this no compact, not necessarily, may not have compact support, may not have compact support. So this is the definition, but then phi naught has compact support C infinity, this is in d omega, you see. So the definition is okay, but then still you need to check the well definedness, trivial, but this kind of analysis you are probably doing first time. Well definedness. What is the meaning of well definedness? Suppose there is another phi 1, suppose I am going bit slowly and writing again. Suppose phi 1 is someone chooses another function, another neighborhood. The only condition is that it should be 1 in the neighborhood of thing. Suppose you phi naught in d omega with phi 1 identically 1 in some other neighborhood, it may be some neighborhood, not necessarily the same neighborhood of k. Okay. Then what happens? Then phi naught is equal to phi 1. So you will have two different neighborhoods, but you still get phi naught is in equal to phi 1 in a third neighborhood, is something like that. If you have a k, so phi naught may be 1 here, phi naught 1 here, identically 1, it may be some other neighborhood, that may be phi 1, but still you get a neighborhood. So here phi naught and will be same as phi naught will be same as phi 1, that is same as phi in that one. So in other words, in this will be in some suitable neighborhood, in some suitable neighborhood of k. And then by our observation, what is it saying, the previous observation, you see, if phi 1 and phi 2 such are in a neighborhood of the support of t, then t phi 1 equal to t phi 2, that implies T phi naught is equal to T phi 1. So it does not matter which phi naught, but it is a kind of a trick you always do, and such kind of function exists, that you know anyway, but that you would have done it in a previous analysis. Okay. And the continuity of T tilde is trivial. Okay. So continuity, you can, if you are not convinced, you can just vary. Continuity of T tilde on E is trivial. Why trivial? If phi n converges to phi in E, that implies phi n phi naught converges to phi naught in D. So and T is continuous. This follows just from the continuity of T. It follows from the and linearity is also trivial, because you can verify that. I do not think anything else to vary. Continuity, linearity. Okay. These are all trivial cases, but first time when you learn is better that you verify. That implies T tilde is in, okay. I will complete the proof and stop it. E prime. Now we want to prove the converse of it, okay, converse. What do you want to prove? This case, right? That is, assume T tilde is in E prime and T is equal to T tilde restricted to D. Oh my God. You want to prove that, and to prove that T is in D prime and T has compact support. We prove this by contradiction. Prove by contradiction. It's like 2-line proof. Contradiction. If not, how do you write? So, any proof by contradiction, how do you write the statement? The moment you write the statement, most of the time things will follow. If not, if T has no compact support, if T has no compact support, what can you conclude? Compact support. What can we conclude from that one? So, you see you have an omega. So, if you choose any compact set here, omega can be written this one, it's a, because Rn is a para compact thing. So, you can choose it as an increasing sequence of compact sets. You can write this Kj j equal to 1 to infinity and increasing sequence. You can choose this always Kj plus 1, and these are all compact. You can write your omega. Since T has no compact support, that is your assumption. So, this is your Kj, and you can always choose a phi j with support here. You can, because, and so we can choose, because Kj is not the supporter, it has no compact support. So, it should give non-trivial values for functions which is supported outside. Suppose T phi equal to 0 for all phi supported outside Kj is essentially means that support of T is Kj. So, that means there exists phi j in d omega with support of phi j is contained in omega minus Kj. So, you see, that is what I am saying. So, you will get phi j supported somewhere here, okay, somewhere support of phi j, okay. And this is more important, and T phi j not equal to 0. So, without loss of generality, assume T phi j is equal to 1. This you can do it. If you are not convinced yourself, if T phi j is not equal to 1, you divide phi j by T phi j, because T phi j is not equal to 0, and so T of phi j by T phi j is a constant, and T phi j will come out and do that one. This in PDE you would have seen it many times. So, that is all. So, what can you tell about now? Okay. Phi j, please note that, you can note that, so phi j, the Kj's are going towards omega. So, the phi j can never converge in d omega, because you do not get a compact set where support of phi j contained. So, phi j cannot phi j is cannot converge to anything in d omega, but then phi j. So, this is an interesting thing to see. So, clearly phi j converges to 0 in E, that is possible, because what is the convergence in E? The convergence is that phi j converges to 0 means phi j and all its derivative go to 0 uniformly on compact sets. So, if you take any compact set and j becomes larger and larger, the phi j support, when j becomes larger, the support of phi j will be outside k j. So, phi j will be and will be identically 0 on any compact set when j large enough. So, all its derivative vanish. So, you get so this is a typical examples which you study a sequence converging into E, but not in. So, that implies, because T is T of E j is a T restriction is same as T tilde of P j, and T delta is a E prime, and hence P j converges to 0 by continuity, this goes to 0. This is a contradiction. This is a contradiction. So, that is done. Okay, that is a proof of that T tilde is in E prime. So, I will stop here. So, in the next class we will see that every distribution with the compact support is of finite order. That is not surprising if you have understood this now, because the support is in K and T is essentially depends only on the support, which is a compact set. So, whatever be the thing for that compact set, essentially it is not exactly, there are some technical small technical thing, and you can see that you can choose an n independent of K, okay, because of this compact nature of that. So, and that will give you the other things. Okay. So, we will prove that next time. Thank you.